we're continuing with section 14.5 and a few directional derivative examples. Example 1. Calculate the directional derivative of f of x and y equal to x to the third y squared plus 7x squared y to the third at point 1 and 1 in the direction of the vector v equal to -2 and 1. Before you forget, the first step that you want to take is to convert that v to a unit vector in the direction of v. So you basically want to divide the v by the magnitude of v. So what is magnitude of v? Magnitude of v is 1 over magnitude of v is -2 to the power 2 plus 1 to the power 2 times -2 and 1, and that is square root of 5, so it's -2 over square root of 5 and 1 over square root of 5. So that's the vector. Now, the next step is to find the gradient vector, the nabla of f. And so the gradient vector is going to be equal to a derivative partial of the function respect to x, which is, this is gradient at x and y. Let's write it down like that. X and y is equal to gradient at x and y is equal to 3x squared y squared, because y squared is the constant, plus x squared, you take the derivative, 2 comes down, so 14xy to the third. And then derivative with respect to partial respect to y, that's 2x to the third y plus 21x squared y squared, because with respect to y, x squared is going to be a constant and x cubed is going to be a constant. Evaluate the gradient vector at the point. Where's the point? The point is right there. And so you get 3, 1 to the power 2, 1 to the power 2 is 3, plus 14 times 1 times 1 is 14, and then 2 times 1 times 1 plus 21. And that is 17 and 23. Now that you found both vectors that you want to dot product them. So the gradient vector dot product and that is equal to as -34 over square root of 5 plus 23 over square root of 5, and that adds up to -11 over square root of 5. So the directional derivative in direction u, unit vector u, is going to be equal to -11 over square root of 5. Gradients and directional derivatives in 3 variables. So let f of x and y and z be a function of 3 variables. The gradient vector of a differentiable function f at a point a and b and c in the domain of f is equal to the partial of f with respect to x at a and b and c, partial of y, partial respect to y at a and b and c, partial respect to z at a and b and c. Those are the 3 coordinates. If u is p and q and r, u equal to p, q, and r is a unit vector, then the directional derivative of f at a and b and c in the direction of u is similarly to what it was in the a function of two variables. It's going to be equal to limit as t goes to 0 of f of that line that contains point P, A, B, C, and in direction PQR minus f of A and B and C over t as t approaches 0. Now, this is similarly, you can see that the formula is going to be gradient of f at A and B and C dot u, basically. Again, the definitions are very similar, and the directional derivatives are basically the formula that you're going to use. This other limit definition, similarly to calculus of one variables, you don't use those for computation. You use them for conceptual part, but then you use the gradient dot the unit vector for the computation of the directional derivative in direction u. Example 2. Calculate the directional derivative of a function f of x and y and z equal to x cubed minus xy squared minus z at point 1, 1, and 0 in the direction of the vector v equal to 2, negative 3, and 6. Again, similarly to what we did for the functions of two variables, we start with finding the unit vector in direction of the v. And so that would be, so first step should be making the v a unit vector. So what would that be? Well, let's calculate the magnitude. Square root of 4 plus 9 plus 36, square root of 49, that's 7. And so u, the unit vector in that direction, is 2 over 7, and minus 3 over 7, and 6 over 7. Now that we found this, let's find the gradient vector x, y, z. See, there's another input, and the first coordinate is 3x squared minus y squared. The second coordinate is minus 2xy with respect to z, negative 1. Now find the gradient vector at the point given. What's the point given? That's a point. Plugging in 1 for x and 1 for y. Again, 1x and 1 for y. And you end up with gradient vector at that point is equal to 2, negative 2, and negative 1. Now, dot product 2 over 7 and negative 3 over 7 and 6 over 7 with that. And it would be 4 over 7 plus 6 over 7 minus 6 over 7 is equal to 4 over 7. And that is the directional derivative in direction u at 1, 1, and 0. I click at question 14.5a. which of the following is a possible value of a gradient of f of a function f of x and y of two variables. So pause the video and think about it and come back. So gradient of f is a vector, and it has as many components as the input of the function. So it cannot be this one or this one or this one. It has to be C.